Hello and welcome to this Estranged development blog video. First thing I wanted to do was acknowledge it's been about 5 years since the last one, so sorry about that. Things happen. I wanted to give you a sneak preview of Estranged Arctic Cold and also talk about buoyancy logic. We did a previous video on buoyancy, but it was all about blueprints, and now we have a more comprehensive buoyancy system, and it's moved into code as well. So I wanted to share the code and talk through it. So what does the buoyancy logic do? Well, it makes things buoyant. It also, though, makes things orient to the kind of correct direction. So the biggest surface area will be flat on top of the water. You see this pallet. It will not allow itself to just kind of bob up and down in the rotation that it lands in the water. It does always try and orient itself. That's intentional, so you can... for gameplay reasons in this level, for reasons you may have guessed already, it means that you can kind of step on these things and move them around to create a little path for yourself. There's no kind of floor is lava puzzle here. It's just a kind of bit of an intro to that. But it could certainly be used to support floor is lava style puzzles. It also supports kind of buoyancy with a hull offset. So you see this boat bobbing up and down. We'll talk about that as well. But the boat is sitting on top of the water rather than, kind of with its center of mass almost, embedded in the water. So, that's intentional because, we don't actually have in this level at least water that can kind of, part around the boat so it doesn't actually go into the boat. That would be a lot more advanced, completely doable, but it's just not worth it, I think, for this level. And you can see it can be capsized if you jump up and down on it, but it will try and self-right itself as well, and it'll try and self-right itself so it's sitting above the water. Although in this case I think it's given up. I think that it's decided that's good enough. Anyway, still tweaking this, but I wanted to kind of share the implementation. So firstly, what I wanted to do is select one of these palettes and just kind of show you what's going on in the data here. So what we have is an EST physics user data, and this was already a thing that I'd added because I wanted to be able to override the mass of objects, because there's no good way to kind of set the mass for the asset itself so that when you drag in the same asset in different levels, it has the same mass. So I added this to do that, to make it consistent. And there's logic in Estranged which kind of reads this out and applies the mass where applicable. So buoyancy coefficient, this is the buoyancy magic number that essentially makes the object buoyant. So if I set this to 1, for example, it'll be less buoyant. And I think it will try and float, but not very well, not as well as it is right now. Let me just... Yeah, you see that it doesn't really do anything anymore. Now it's kind of at equilibrium with the water. If I go ahead and tweak it down even more, so we say it's 0.5, then things will sink. So that's exactly what that's doing. If I tweak it way up as well, I say it's 64, this should be entertaining, things should, shoot up into the air. There you go. They're building momentum. Isn't that great? I guess, I'm not really sure how that's useful, but, it's fun. Maybe we could put some music behind this and choreograph it. Anyway, not really for this level, so let's set it back to 1.5. Buoyancy coefficient 1.5. We've also got the self-righting degree, so that's the behavior that I showed you where it tries to orient itself so the largest surface area is kind of flat on the water. So this is a hack, basically. I mean, real buoyancy, it's kind of, forces operating on the whole object. So kind of naturally it orients itself so the largest surface area becomes kind of, flat on the water. This is trying to simulate that in a very cheap way because actually there's only one force here. There's only one buoyant force operating on the object as a whole. So this is kind of to work around that. There's also a hull offset, and that's how the boat works. So if I set the hull offset here to 120 centimeters, for example, then the pallets will float above the water, and they'll actually exit the water, which is which is kind of weird. Yeah, that's not the behavior you want. This one's having fun. Okay. So let's reset that, because palettes don't need that. The center of mass is already correct. Okay. And lastly, I just wanted to show you how this is actually working in the editor. So if I select one of these, this works on static meshes and skeletal meshes. I'm using skeletal meshes here because of capsule shadows. I'm kind of playing with those, but it also works on static meshes as well. I just add this physics effects component, and the physics effects component is responsible for taking that physics user data that's defined in the asset. So things like buoyancy control, so the buoyancy and the mass, that this is all consistent wherever this asset is used, so long as you add the physics effects component to the mesh when it's in the level. So I've got a map check actually that says, if you've got a static mesh or a skeletal mesh that's simulating physics and you don't have the physics effects component, I get an error in the log. So there's kind of protections against forgetting to do this, because it's also responsible for impact effects and that kind of thing. So I'm going to switch over to the code now. And this is actually the source code for the physics effects component. All of this is on GitHub under the Estranged core repo. So what I'm going to do now is kind of show you what's going on here. So when it's set up, this onRegister call, which is called, as I found at some point, and was caught by, it's called multiple times because of, various things being run in the editor multiple times. So you need to be idempotent with this method. But this kind of sets up the meshes and it also works on kind of breakable chaos stuff, which is not something I'm going to demo in this video. But it sets up all of the delegates to listen to things like, okay, overlap events, hit events, and here's the chaos stuff when things break. So we can play, impact effects, sounds, that kind of thing. So it's responsible for all of that. We've got a kind of begin overlap. So what it's testing for here is whether it's in a physics volume. And in Estranged, all of the water are physics volumes. So that usually means that, it will have this water volume Boolean that's true. And then if it is, it sets some damping. So that's pretty important. If we weren't setting damping here, then things could have the potential to kind of spin around a little bit, be a bit unstable. And the idea is that the water is adding some kind of fluid friction to everything. So it is adding that damping. So that's what we're trying to simulate with this. These are kind of arbitrary numbers, but that's what we're trying to simulate here, that the water is slowing things down. Adding a kind of fluid around things. So what we do every frame then, if we are in water, is that we apply a buoyancy force. So the first thing that it wants to work out is the kind of water plane. And currently this logic does not deal with water that is not flat. So something to add in the future, but right now it doesn't need to deal with water that's not flat. If we have a proper water volume, and what I mean by that is an estranged water volume, then get its config. The reason there's an estranged water volume is because, let me actually show you this. The estranged water volume has certain things. So it has this data asset here, ocean water. So if I open this up, it's got a sound mix override when you're underwater, which kind of muffles things. It also kind of turns off the reverb. It's got a camera modifier. It's got, camera modifier when you're just kind of paddling. When you're under the water, there's a camera modifier. So lots of different settings for this water. And the reason it's set up this way is that you can just share this data asset for ocean water, in another level that needs ocean water. So it really helps. But what it also has, and don't ask me why I put it directly on the volume, I might move it into the data asset later, is buoyancy wave frequency and buoyancy wave amplitude. This is not actually hertz. I was trying to be fancy and give it a unit, but it's not actually hertz. But this is kind of saying, I want every 1.5 seconds the peak of the kind of wave to be 3 centimeters. So I want the kind of object in the water to be elevated 3 centimeters above that water to kind of give the impression that, there's waves here and things are bobbing about. So that's what you're seeing here. It could be a bit more random. I mean, right now everything is kind of orchestrated together and it looks weird. So I'll probably add some kind of noise to this, and probably make it a little bit more intense as well. But that's the intent behind this. The other thing that thwarts it a bit is when you enable debug primitives. This is a feature in this build of Estranged, which may be familiar to those who have used the source engine. Sometimes the physics actors, and I don't see it happening here. See, these are asleep, state asleep. These are awake because they are having kind of force exerted on them. Sometimes the things in the water go to sleep, which means that the bobbing stops. I think it's probably because they peek out of the water a bit, but yeah, it's something to watch out for, which would kind of stop the bobbing. As a side note, I did have this bug that things would go to sleep while the player was holding them, which was quite frustrating. In fact, you can see that. I hadn't appreciated that. So when I'm not moving, you can see the state is swapping between awake and asleep. So perhaps there is still a bug here and the velocity's kind of jumping around a little bit in a way I wouldn't expect. So maybe there is still a bug here. I mean, what's happening here is when you're moving around the held actor, every frame, my code is saying, keep this object awake so it doesn't stop in midair, because that was happening and that was a bug. But I think I still have work to do here, and I only realised that until this point, so that's fun. Maybe make a bit video around that and what's going on there. Okay, so that's essentially the kind of wave logic, if you like, that we've got here, the bobbing logic. We've also got some kind of calculations in here around the bounds of the object, its current rotation, what's its local down coordinate or rotation, and also this hull offset. That's where we're pulling the hull offset out of the physics user data. And then what we're doing, we've got some early outs here where, if it's not submerged, then ignore. If there's no mass, then ignore. What we're doing here, though, is calculating how much of the object, based on its bounding box, so basic calculation, is submerged. And then calculating the force based on that. So the mass times the inverse of the gravity, taking into account that submerged percentage, and then this buoyancy magic number, which is kind of operating on it. And then finally, we end up with a total force, and we apply that just to the primitive component. So that's how that's working. And obviously this is constructing a vector which is pointing directly up. So there's an additional piece of logic here as well around self-writing. So if the self-writing degrees is set, then it will kind of figure out, okay, well, what's the closest rotation to making this correct? In other words, should I rotate it up or should I rotate it down? And you can see that in action when I use the palette here. So if I go ahead, see, it figured out, okay, down is the best rotation there. Maybe I can get it to rotate up a little bit. No, maybe like this. Well, anyway, you can see it there. It's rotating to the up orientation. So that's what this is doing. It's kind of figuring out, what's the closest way to get to up, or the least rotation to get to up. Then it's figuring out, okay, well, what's the delta? How much do I have to do? And if it doesn't have to do anything, it doesn't do anything. And there's a kind of tolerance here. So actually, if I look at the palette, I think I've set it to 10 degrees. Yeah, 10 degrees. I could change this and say, well, if I turn this off, we should probably just turn it off to kind of see what happens. Oops. But if I go ahead and turn it off. There you go. See, that's just kind of chilling out, hanging there, but it's not what you'd expect, because you'd expect the water to kind of operate on the full surface area of it, and it to be buoyant that way, and it to sit on the water. So there's also a kind of unnatural self-writing degree. So actually, if I just say 0.1, the tolerance is 0.1. Then it will try and rotate itself to exactly kind of upright, which looks a bit unnatural as well. It looks a bit mechanical. So there's a good kind of middle ground, I think, in 10 degrees. See, that is completely upright. That has rotated it to the absolute most upright it can be within 0.1 degrees. So I think 10 is a good compromise there. So that's what this logic is doing, and you know, at the end of this, it's kind of calculating some torque in radians to apply to the primitive component in exactly the same way that we're applying force to it to make it buoyant. So that's pretty much it for this video. Like I said, thank you for watching this kind of preview of Arctic Cold, and I hope to make more videos in the near future. Thank you.